Hi everyone, welcome back. Let me take another example. Consider this language. Okay, so with respect to this language, which strings are distinguishable? Option A. Tell me which strings are with respect to this language. This is okay. With respect to this language, which of these strings are distinguishable? Tell me. Can I say A comma B? Can I say A comma B? These two strings are distinguishable. Can I say they are distinguishable? Can I say these two strings are distinguishable? Do we have any Z? Do we have any Z such that one will go to language, another will not go to language? Do we have any Z? Does there exist any Z? Does there exist any Z such that one will go to L, another will not go to L? Do we have any Z? Tell me. No. There does not exist any Z. Not possible. Not possible. There does not exist any Z because for all, because you can notice that for all Z, can you notice that this does not belong to L? Also, this does not belong to L. Whatever Z you take, you can notice they don't belong to L. So I can say A comma B are not distinguishable. Is it clear? Is this clear? Tell me, is this clear that A comma B, these two strings are not distinguishable because whatever you do, whatever Z you put here, whatever extension you put here, they both will they both basically don't belong to L. Okay, now so similarly this also, but these are distinguishable. Tell me why they are distinguishable. Why epsilon comma A are distinguishable? Who is distinguishing them? Yes, who is distinguishing them? There exists a Z and that Z is epsilon. That Z is epsilon. Yes, very good. Similarly, who is distinguishing them? Epsilon comma AB. Who is distinguishing them? So I can say distinguishing extension. Distinguishing extension. Okay, distinguishing extension. What is that? Extension. That means Z equal to epsilon. So there exists a Z. You can notice that. If you take this Z, then you can notice that epsilon Z belongs to L and AZ that does not belong to L. Similarly, if you take this Z, you can notice epsilon Z belongs to L and you can notice ABZ does not belong to L. So tell me, is this concept clear? With respect to any language, can you find which strings are distinguishable, which strings are not distinguishable? And what about this language? Let's assume this is your language L. Tell me, what can I say about strings? Who are distinguishable, who are not distinguishable? Can you give me two strings which are distinguishable? The answer is every two strings are not distinguishable. Okay, whatever two strings you take, yes or no? Every pair of strings that is basically strings is non-distinguishable. Yes or no? with respect to L. Because whatever two strings you take, any two strings you take, any two strings, that is your choice, any two strings you take, now for all Z, what will happen? It will happen, for all Z, it will happen that this will happen. For all Z, this will happen. For all Z, they will belong to L. Correct? Whatever two strings you take. Let us take another example. Sigma star is equal to A power n, B power n is greater than equal to 1. Tell me, which strings are distinguishable? Find the distinguishable strings with respect to L. Let's assume this is your language L. With respect to L, so which are okay? Tell me, are they distinguishable? Are they distinguishable? Tell me. With respect to this language L, which are distinguishable? Which strings are distinguishable? Are they distinguishable? Are these two distinguishable? Who is distinguishing them? Who is distinguishing them? Are they distinguishable? Yes. Who is distinguishing them? B. Yes, very good. They are distinguishable and Z is equal to B. Z equal to B. Okay. Z equal to B will distinguish them. Are they distinguishable? Are they distinguishable? Yes, they are distinguishable. Epsilon will distinguish them. Yes, they are distinguishable because epsilon will distinguish them. See the language. You are not looking at the language. You are not paying attention. Pay attention. Okay. So who will distinguish them? For these two strings, Z equal to epsilon will distinguish them. And tell me, these two, are they distinguishable? Yes. Who will distinguish them? B. For these two, Z equal to B will work. Z equal to B will work. And for these two, are they distinguishable? They are not distinguishable. You can notice they are not distinguishable. Because whatever W you take, actually, for all Z, what will happen? For all Z, you can notice this does not belong to L. This also does not belong to L. So they are not distinguishable. So they are not distinguishable. Okay, whatever Z you take, they do not belong to L. For all Z, they do not belong to L. So you cannot distinguish them. And what about A square, B square, A power 4, B power 4? What about them? A square, B square, A power 4, B power 4. You can notice they are also not distinguishable. You can notice they are also indistinguishable. Why? Because if you take epsilon, if you take Z equal to epsilon, then they will both belong to L. Yes or no? If you take Z equal to epsilon, and if Z is anything other than epsilon, if Z is epsilon, both belong to L. Both belong to L. If Z is anything other than epsilon, then both do not belong to L. Okay, yes or no? Can you notice basically this distinguishing strings actually, okay, in movie terms actually you can see jiyenge saath marenge saath. It's something like this. Okay, so basically two friends are there. Okay, this is W and this is X. Okay, now let's assume they are in this world. In life L, they are okay together in life L. You know, there are 7 lives. I think in Hindus there are 7 lives. I don't know. Okay, maybe. Okay, so they are in this life L. So this life L, this is your language. Okay, this is your language, and these are two people, and they are friends. Now let's see whether they are true friends or false friends. If they are true friends, then what will happen? If they are true friends, then it will happen that whatever problem you comes, whatever Z, this is the problem. If they are true friends, then whatever problem comes, either they will both die or they will both live. Basically, they will be together. Either they will both go to jail or they will both not go to jail. It's like this. Okay. So either, okay, for all problems, for all strings, either they will both go to jail. Okay, either WZ, XZ, either they both will go to jail, or like either they will both go to L, means they live. Okay, जिएंगे तो साथ, मरेंगे तो साथ. Okay, so either they will both live, or they will both die. Okay, this is called जिएंगे तो. Okay, in movie terms, this is called, in Hindi, this is called जिएंगे तो साथ, मरेंगे साथ. In English, what is called? So this is your L. So either they will both belong to L or they will both not belong to L. Okay, जीना साथ, मरना साथ, something like this. Something like this. Live together, die together. Yes, oh, yes. Live together, die together, basically. Yes. Okay. So this is your live together, die together. Okay. Now, okay. So these are true friends. True friends mean they are indistinguishable. They are indistinguishable strings. Means they will live together. They will also, either they will both belong. Okay, whatever problem comes in life, either they will both live, or either they will both belong to L, or they will both not belong to L. Now let's assume they are not true friends. Okay, they are not true friends. Then what it means? They are not true friends. Not true friends. It means they exist. There exists a problem. Maybe, okay, on some problem they are together, but there exists a problem where one will die, one will live, something like this. Okay. Now, are you getting my point? With respect to life L, okay, with respect to life L, so there are two friends, okay, and there are two friends which are from sigma star, and with respect to life L, if they are not true friends, it means there exists a problem such that one of them will die, one of them will live, another will die. Okay, so it means it's like this. So now is it clear? Now some intuition, some visualization can you do? Now you can do some visualization, I hope. The concept that we have. Okay, so now tell me which of, okay, you can notice they will die together. Actually, whatever problem comes, they will die together. They will not live, they will die together, whatever problem comes. And what about them? A square, B square, A power 4, B power 4. You can notice if this problem comes, they will live together. If any other problem comes, they will die together. But live together, die together. Yes or no? And what about them? AB, A square, AB, what about them? Which problem will differentiate them? Which problem will show their true face? Tell me, which problem will show their true face? They are friends, but which, okay, yeah, yes, there exists a Z equal to epsilon will show their true face. You can notice this Z does not belong to L, and this Z belongs to L. So they are indistinguishable. So they are distinguishable. Is this clear to everyone? Tell me. The concept is clear with respect to L. So which strings are distinguishable, which strings are not distinguishable? Okay. Now let's see. The Myhill Nerode Theorem. Actually, This Myhill Nerode theorem is very interesting actually. Why this is interesting? Let me tell you. Why this Myhill? Okay, let me tell you why this. There is a theorem. This we will study. Yes, today only Myhill Nerode theorem. Why this Myhill Nerode theorem is interesting? Because this is a theorem. I will tell you the statement. Let's assume this is a theorem. And if you have a regular language, then actually you can prove regular, non-regular both. Basically, if you have regular language, then something will happen. If something will happen, then there will be regular language. So it's a two-way theorem. I will tell you, don't worry. So let's see what is this Myhill Nerode theorem. First, you understood the distinguishable and non-distinguishable string that you understood. Now the statement is this. Okay, so two strings. Now the very simple thing. Okay, so this example you can do ends with 1 0. Let's see this language. With respect to this language, W ends with 1 0. Okay, so tell me, with respect to this language, let's check 0 1. Let's check these two strings. Are they distinguishable with respect to this L? With respect to this L, are they distinguishable with respect to L? Who will distinguish them? Tell me. Who will distinguish them? W equal to, yes, W equal to epsilon will distinguish them. Sorry, Z equal to epsilon. No, Z equal to not epsilon. Z equal to 0 will distinguish them. Z equal to 0, that will distinguish them. So they are, you can very easily see. And what about 0, 1, 0, 0? With respect to this language, what can you say about 0, 1, 0, 0? What about 0, 1, 0, 0? Can anyone distinguish them? W ends with 1, 0, 0, 1, 0. Can anyone distinguish them? You can notice no one can distinguish them. You can notice. Okay. If it is going to language, means if it is going to language, it means it is ending, it means this Z is ending with 0, 1, 0, yes or no? If this is going to language, it means Z is ending with 1, 0. It means Z is ending with 1, 0. Okay. If Z is ending with 1, 0, then this will also go to L. Yes or no? So very simple. They will live together, die together. So they are indistinguishable. Clear? Okay. Now what we are going to do? We are going to do some mathematics, discrete mathematics. You know equivalence relation or not? You know equivalence relation? So now I am defining an equivalence relation on sigma star. Okay. So this equivalence relation I am defining. Focus on this equivalence relation. Now on sigma star, remember our base set is sigma star. So our base set is sigma star, means set of all strings. Now I am defining with respect to some language. So I am defining this equivalence relation. You can notice with respect to some language. Okay. So basically my relation R, I am defining a relation R on sigma star with respect to L. Okay, I can say that with respect to L. So I am defining this on sigma star. It means my relation is from sigma star to sigma star. Correct? Correct or not? Or I can say that my relation is basically subset of sigma star cross sigma star. Correct or not? Do you remember this point? All these things. Equivalence relation. We have already seen. So my base set is sigma star. I am defining a relation on sigma star. And how I am defining? So I have a language. Let's assume I have some language. Some language is given to me. And my relation is like this. String W relates to string X if and only if there is, if and only if for all Z this is happening. For all Z this is happening. What is happening? If WZ if wz belongs to L, then xz also belongs to L. And if this does not, so basically this is happening, means live together, die together. Okay. So two strings in sigma star, remember, my base set is sigma star. My base set is sigma star. So two strings in sigma star, remember W comma X, they belong to sigma star. There are any two strings in the sigma star. What I'm saying that they are related if and only if they are true friends. Yes or no? If and only if they are true friends. It means for all problems, whatever problem comes, either they will both live together or they will both die together. So basically W comma X, they are, I can say W comma X are, W is related to X if they are true friends. This is okay. Now let's check it out. First you tell me, is this okay? So remember some language is given with respect to some life. Now tell me, first you check, is it reflexive? Let's check whether it is equivalence or not. Is it reflexive? Can I say W? Yes, of course, because whatever Z you take, this if and only if this, either they will be both in the language or they will both out of the language. Is it symmetric? Again, yes, die together basically, again symmetric because W belongs to X, automatically means the X belongs to W. No problem. Okay, this is symmetric, right? If they are true friends, if W comma X are true friends, then X comma W are also true friends, no problem. Okay, so if this is happening, then this will also happen. Is it transitive? Is it transitive? Let us check. So let's assume W is related to X, assume X is related to Y. What it means, whatever Z you take, what it means? It means whatever Z you take, let's assume you take some Z. Let us assume both belong to L. Now you take this Z. Now basically Z is any string. You can take any Z that you want. Okay, any Z you take. Can you notice? Either they will together in L or they will not be in L. Similarly, XZ already belongs to L, and Y automatically, because they are related, so YZ belongs to L. Now from here, can I say W comma Y? Yes, I can say W comma Y, right? Yes, I can say W comma Y because you can notice WZ belongs to L, you can notice YZ belongs to L. So you can notice that I can say this. So remember, either this will happen if you take any Z, either this will happen or this will happen. Either this will happen or this will happen. So you can notice this is transitive, yes or no? Is it clear to everyone? So finally, we have proven that this is transitive also. So this relation that we have defined, this equivalence relation that we have defined, this is transitive, correct? Now let's find how many equivalence classes will be there. This is interesting question. Answer is depends on L. Yes or no? Answer depends on L. Depends on the language L. Now let's take a language L and so that okay, so let's take a language L. Let me give you language L and you tell me how many. Okay, this equivalence relation you define. This equivalence relation you define and you tell me this. So this is your language. Tell me A comma B A. Okay. Now tell me how many equivalence classes. How many equivalence classes of this relation? I have not told minimum. Okay, Vidyasagar, just apply this relation. Just apply this relation. I know many people are very knowledgeable, but apply this relation. How many equivalence classes of this relation? Let me check. Okay, just let me check. Can I say A is, tell me, A is related to BA or not? Is it true? A is related to B, this string. No, they are not related, right? Who will distinguish them? Who will distinguish them? They are not true friends. A comma BA, they are not true friends. They are not true friends. They are not true friends. No, epsilon will not distinguish them. A comma B, how can epsilon distinguish them? If you put epsilon, then they will both go to L. If you put epsilon, if you take Z equal to epsilon, if you take Z equal to epsilon, then they will both belongs to L. Both belongs to L. So who will distinguish them? Who will distinguish them? Is there anyone who can distinguish them? Is there anyone who can distinguish? Actually, no one can distinguish them. Yes. Actually, no one can distinguish them. Wait a second. A. Is there anyone who can distinguish them? A. Yes, no one can distinguish them. Correct? You can notice no one can distinguish them, because if you add anything, okay, for example, epsilon cannot distinguish them. If you add anything, then that also cannot distinguish them. Apart from this, if you add anything, then both of them do not belong to L. Yes or no? Both of them, they do not belong to L. So they are definitely related to each other. So they will belong to same equivalence class or not? So can I say they will belong to same equivalence class? Yes, because they are related. So they will belong to same equivalence class C1. Let's call it C1. Is there any other string which will come here? Is there any other string which will come here? How can you say that no string will come now? No other string can come here. Why? Because of epsilon. Yes or no? No other string can come because of epsilon. So this is the simple point. No other string comes to this C1 class. Comes to this C1 class because of epsilon. Yes or no? So can I say this is the only equivalence class? Can I say my base set? Is this my base set? Is this my base set? Can I say from my base set all strings are covered? Can I say from my base set all strings are covered? So only one equivalence class? No, base set is sigma star. Please. Base set is not L. Base set is sigma star. This is what I am saying. This relation that we have defined, this is relation on sigma star, not on L. This is relation on sigma star, not on L. So this relation is with respect to L. Basically, this relation that we have defined, we are saying that W is equivalent to, W is related to X if and only if. Remember, this W comma X, they are any strings. They can be any strings. So my base set is sigma star, not L. Remember, base set is this, not L. So they can be any string, whatever strings you can have here. When I will say that they are related. This is my relation. My relation is this. If and only if for all Z, WZ belongs to L, if and only if XZ belongs to L. So remember, this is equivalence relation on sigma star, but with respect to L. So friendship you will see with respect to L, remember. Okay, the friendship you will see. Okay, friendship of two people from here. So elements will come from here. Elements of this. Okay, and their friendship you will check with respect to here. Yes or no? Elements of this sigma star, elements of this base set, their friendship you are checking with respect to L. Is this clear? Now is it clear? Tell me. So my, remember, this is not a base set, remember. So for this I can say L is not base set. Sigma star is base set. So tell me, this equivalence class we got, but we will have some more equivalence classes, yes or no? Because all the elements in sigma star, they must go. Now where are they going? Okay, so one equivalence class I got is this. This is one equivalence class I got. Any other equivalence class? Can I say epsilon? Okay, just tell me this point. Epsilon comma B, where they will go? Will they go together? Are they equivalent? Just think about it and tell me. Can I say they are equivalent? Epsilon comma B? Can I say? No, right? No, because Z equal to BA. Take Z equal to BA. Take Z equal to BA. So they cannot go to same equivalence class. These two cannot go to same equivalence class. Is there anyone who can go with the same equivalence class as epsilon? If I put epsilon here, can I put anything else? Can I put anything else here? I cannot put anything else here. Why? Tell me why. Epsilon is not related to anyone actually. It is not related to any string. Why? Because of BA. Yes or no? Because of Z equal to BA. Because of this BA, you cannot put anything. Whatever you put, if you put anything, if you want to put anything, you cannot put because of this Z equal to BA. Correct or not? So this is another equivalence class. This is another equivalence class. Okay. Now, where can I put B? Now, let's assume B is here. What else I can put here? Tell me. Can I put anything else here? With this B, can I put anything else here? These are already over. Anything else? Can I put anything else here? Tell me. Can I put anything else here? Why I cannot put? You cannot put anything else here. Why? Because of A. Yes, very good. You cannot put anything else here because of A. Cannot put more strings due to A. Because of A. Because if you put anything else here, so for example, this B, you can notice if you put anything else here, let's assume, let me put A is already over BA. Let me put this. Can I put this? I cannot put this. Why? Because of A. You can notice because of A. So this is another equivalence class. Is there any other equivalence class? Yes. All other will go to same. All remaining strings, they will go to same equivalence class. Now I can say the rest of them will go to this equivalence class. The rest of them. So how many equivalence classes I got? For this language, how many equivalence classes I got? 4 equivalence classes. So for, okay, this is your language. Your language is A, BA. This is your language. Now you can notice that this relation on sigma star will give 4 equivalence classes. It will give 4 equivalence classes. In one equivalence class, you will have A, EB. In another, you will have this. In another, you will have this. In another, you will have rest of the strings. Yes or no? Because rest of the strings, they are equivalent to each other. Whatever 2 strings you take, they are equivalent to each other. Okay, now a very interesting thing is coming. Okay, excellent thing is coming. Just make DFA for this. Hare Krishna, this is confusing because this is the first time you are studying. Once you solve 5 or 10 examples, it's over. In the GATE exam, can they give you this equivalence relation? Can they define this equivalence relation? Yes or no? In the GATE exam, they can give you, okay, that on sigma star, we are defining this equivalence relation. The definition they can give you. Okay, and then they can ask you some questions. Yes or no? Now tell me. Okay, so for equivalence, okay. Now let's create DFA for this language. Quickly create DFA. Minimal DFA. Let's create minimal DFA for this language. Create minimal DFA. Create minimal DFA for this language. BA should be accepted. A also should be accepted. And this is dead state. Yes or no? So how many states will be there? 4 states will be there. Can you notice? Okay, let's call it P, let's call it Q, let's call it R, let's call it S. Tell me what are the strings that are coming on P. Just tell me what are the strings that are coming on P. Let's call it LP. Means what are the strings that are coming on P? Only empty string. Yes, very good. Only empty string is coming on P. What are the strings that are coming on Q? Strings that are coming on Q. Only B. Very good. What are the strings that are coming on R? Strings that are coming on R. BA, A. Yes, very good. A, BA. And what are the strings that are coming on S? The rest of the strings. Yes or no? The rest of the strings. Can you notice very interesting thing? Every state in the minimal DFA, can you notice one interesting thing? These equivalence classes that we have created, 4 equivalence classes we have created, and in the minimal DFA you have 4 states. You can notice that each state is basically corresponding to one equivalence class. This was our equivalence class, this was equivalence class, this was equivalence class, this was equivalence class. Is it clear to everyone? Can you see this interesting thing? Very interesting thing. Okay, so let's take another example. Don't worry. Okay, many examples we will do. Don't worry. So let's take this example. Okay, so A, BA we had taken, right? Now let's take A, AB. Okay, so tell me how many equivalence classes of, this is the question. How many equivalence classes of this relation? How many equivalence classes of this relation? Think about it and tell me. For practice, do like this, or don't create minimal DFA. Please don't create minimal DFA. For practice, for your practice, for your knowledge, create like this, like the way I did. Tell me, are they true friends? Are they true friends? They are not true friends. You can notice they are not true friends. Why? Because Z equal to B, this problem, once this problem comes in the life and they are gone, one will be alive, another will be dead. So this problem will differentiate them, yes or no? So they are not true friends. If this is going here, then this will go here. So 2 different equivalence classes, they will go, yes or no? I can say that A, this is not related to AB. A is not related to AB. So they will go to different equivalence classes. Can I write anything else here? Can I put any other string here? Can I put? No, because of epsilon. Because of epsilon. Can I put anything else here? No, because of epsilon. Very good. No, because of epsilon. I cannot put anything else here. I cannot put anything else here because of epsilon. Okay, so now tell me where the remaining. Okay, can I put with the empty string? With the empty string, can I put something else? with empty string, can I put something else? I cannot put with empty string. Tell me, are they related? Are they equivalent? Are they related? No, they are not related. Z equal to A will differentiate them. Z equal to A, yes or no? So can I put anything else here? You cannot put because of AB. Nothing can be put because of AB. Because of AB, you cannot put anything else here. No string, no more string. Yes or no? Tell me. Because of AB, no more string can come here. Okay. Anything, any other equivalence class? Okay, so this is over. A cannot come because empty string will distinguish them and nothing can come. Okay, now tell me. So these three equivalence class, we got this equivalence class, we got this equivalence class, we got this equivalence class. Where are the remaining people? Where is B? All the remaining people, they will go to same state, yes or no? All the remaining people, actually all the remaining people, they will go to same state, correct or not? You can notice all the remaining people will go to same state. So finally, how many? Okay, for this language, this is our language A, AB. And you can notice for this language, this relation on sigma star has how many equivalence classes? Has 4 equivalence classes. And what are those? This is one equivalence class, this is another equivalence class, this is another equivalence class, and the remaining strings, rest, okay? So these are. Now tell me, create the minimal DFA for this language. Let's create the minimal DFA. What you will get? Create minimal DFA. What will you get? Now can you notice? Okay, let's call it P, let's call it Q, let's call it R, let's call it S. Now quickly tell me, what is the language of P? What are the strings that are coming on P? What are the strings that are coming on P? Only empty string is coming on P. What are the strings coming on Q? Only A is coming on Q. What are the strings that are coming on R? Strings that are coming on R. Strings that are coming on R. Only AB. Yes, very good. Only AB. And what are the strings on S? The remaining, yes or no? The remaining strings. Correct? Can you notice each state corresponds to one equivalence class? Each state is the language of each state. The language of each state is same as equivalence classes. This was our equivalence class, this was our equivalence class, this was our equivalence class, this was our equivalence class. Is it clear to everyone? Okay, so let's take this example. A power n, B power n, n greater than equal to 0. And for this language, let's see how many equivalence classes. Okay, for this language, how many equivalence classes? Of relation of this relation. How many equivalence classes for this language? This is your language, and with respect to this language, how many equivalence classes of this relation? Okay, yeah, actually you don't have to do. Let me tell you. Can you notice? Just tell me this point. Can you notice? Every string of this set will go to different state. Okay, this point can you observe that every string of this set, they will go to different equivalence classes. They will go to different equivalence classes. Tell me. This is the only point you need to understand, that whatever two strings you take, for example, whatever two strings you take, a power 10, a power 15, then they are indistinguishable. Yes or no? Who will distinguish them? Z equal to b power 10 will distinguish them. Yes or no? Z equal to b power 10, that will distinguish them. So they are not true friends. A power 10, a power 15, they are not true friends. Okay, so this is the point you need to understand, that from this set, actually you can put epsilon also here. Can you notice from this set, every two, each of them are going to different equivalence classes or not? They are going to different equivalence classes or not? This you can guarantee. They will go to different equivalence classes, correct? Can you guarantee this? Yes. Okay. They are going to different equivalence classes. So what can I say about number of equivalence classes? Infinite. So this itself tells me, so number of equivalence classes, what that will be? Number of equivalence classes will be infinite. Can you notice this is not a non-regular language? This we have already seen. Do you remember this type of set we used to create? Can you relate all the concepts that we have seen in today's class? In today's class, all the concepts that we have seen, can you relate now? Do you remember in the first half, this type of set, this type of infinite set we were creating? This type of infinite set we were creating to prove non-regularity. To prove non-regular, this type of infinite set we were creating. Now, can you notice this? Can you notice basically, I can say number of equivalence classes is infinite. Yes or no? Okay, so that's it. So one thing I can say is number of equivalence classes is infinite. For this, okay, number of equivalence classes will be infinite. But let's, okay, this is okay. Now, just tell me this point. Will these strings go to, okay, just take, okay, these. In this equivalence class, what string you will put? In this equivalence class, what other string will come? In this equivalence class, what other string will come? In this equivalence class. Yes, you can notice a square, b square will also come. You can notice a cube, b cube will also come. A power 4, b power 4 will also come. Can you notice? They are all friends. Epsilon will also come. They are all friends. Yes or no? They are, all of them are friends. So this equivalence class we will get. Yes or no? Okay. In this equivalence class, what strings will come? Tell me. In this, okay, this string, who is friend of this string? Who is a friend of this string? Can you notice this is friend of this string? No, not all remaining. See, this is not friend. This is not friend of this string. They are not friends. They are not friends. Yes or no? These two strings are not friends. So can you notice these strings are friends? All these strings are friends. Yes or no? Correct? All these strings are friends. Are they friends? A power 3, B power 2. Okay, sorry. A power 5, B power 2. Is it friend? Like, is it friend with A power 5, B power 3? Are they friends? Are they friends? No, because Z equal to B power 3 will distinguish them. Now let me tell you, for this language, if you see this language A power n, B power n, and greater than equal to 0, you can notice we have infinite number of equivalence states, equivalence classes. We have infinite number of equivalence classes. Equivalence classes of this relation. For this language, okay, for this language, we have infinite number of equivalence classes. Now you can notice there is an equivalence class where all these will be there. For example, there is an equivalence class in which they will be there, A power n, B power n. all they will go to same equivalence class. You can notice all of them will go to same equivalence class. Yes or no? All of them will go to same equivalence class. Similarly, all of them will go to same equivalence class. Similarly, all of them will go to same equivalence class. Tell me yes or no? Like this, you can create infinite number of equivalence classes. Yes or no? No, no. This n is any greater than equal to 0. Like this, you can create any number of equivalence classes. For example, you can create a power n, b power n minus 4, a power n, b power n minus 5, a power n, b power n minus 6, and so on. How many equivalence classes you can create? Tell me. Just keep going on. A power n, b power n minus 100. Hare Krishna, n is not a fixed value. Like this, n minus 100, n minus 200, n minus 300, n minus 1 lakh, n minus. Just keep going on. Like this, you just keep going on. N is not a fixed value. Actually, this is infinite, but how do I convince you? This is infinite. Basically, whatever, see, this is infinite. Okay, let me tell you. This is infinite, yes or no? A power n, b power n, they are all here. Okay, a power n, b power n minus 1, they are all here. A power n, b power n minus 2, they are all here. Like this, a power n, b power n minus 1, 0, 0, 0, they are all here. Okay, like this, a power n, b power n minus, you can put any natural number here. That is the simple point. Okay, you can put any natural number here. Any natural number here you can put. So can you see there are infinite? There are infinite. You can put any natural number here. You can put any natural number here. Array infinity is not a natural number, but this is a natural. See, tell me, is this infinite set? Tell me, is this infinite set? Is it infinite set? Hare Krishna, is it infinite set? But there is no infinity here. So is it not infinite, or but there is no infinity here? Yes, this is infinite. You can keep going on. If you have n, then you have n plus 1. If you have n plus 1, then n plus 2, and so on. Like that. Like that, you can keep going on. You can put any natural number here. Or you can understand like this. Or just understand, okay, leave everything. Just understand like this. That all of them are going to different equivalence classes. Take this set. You can notice all of them are going to different equivalence classes. Every element of S, I can say, every element of S goes to different equivalence class. So we have infinite number of equivalence classes. Okay, so here we have infinite number of equivalence classes. If you have infinite language, then will you get infinite number of equivalence classes? Can you say that if you have infinite language, then you will get infinite number of equivalence classes? No. Take this language. How many equivalence classes you will get? Tell me. How many equivalence classes of relation? How many equivalence classes of this relation? Only one. The answer is only one. Only one equivalence class. In that equivalence class, you have all the strings. All the strings you have here. In this equivalence class, all the strings are there. Because Everything is related to everything, yes or no? Every element of this is related to every element of this, yes or no? Can you notice? Because, okay, for this language, if your language is this, now what I can say that whatever two strings you take from sigma star, you can notice that they are related. Whatever two strings you take, correct? Not correct? Let me take this example. Can you see how many equivalence classes are there? Only one. And in the minimal DFA, how many? In the minimal DFA, how many states you have? One. This is not a coincidence. Can you see? Whenever we are getting finite number of equivalence classes, in the minimal DFA also we have that many states. Okay, just take this example. Okay, let's take this. Take this W such that length of W is equal to length of W mod 3 is equal to 0. Okay, let's check it out. How many equivalence classes? This is the question. This is your L. Now on this basically, now this is your L. Let's call it L. Now on sigma star we define this relation. We define this relation, okay, with respect to L. Then how many equivalence classes of this relation? Tell me. How many? How many equivalence classes of this relation you will get? The language you can see. Yes, 3 equivalence classes you will get. You can notice you will get only 3 equivalence classes. Okay, you will only, okay, 1 equivalence class you will get where remainder is 0, 1 equivalence class you will get where remainder is 1, and 1 equivalence class you will get where remainder is 2. In this equivalence class, you will get this string, you will get this string, you will get this string, you will get this string. Yes or no? Because can you notice that these two strings, can you notice this string and this string, can you notice they are indistinguishable? Can you notice, yes or no? They are indistinguishable. Either they, okay, whatever Z you take, either they will both belong to language or they will not belong to language, yes or no? Whatever Z you take, either they will both have length multiple of 3 or they will both not have length multiple of 3. So this is your equivalence class. Another equivalence class will have these strings. These strings will be in another equivalence class, and these strings will be in another equivalence class. So only 3 equivalence classes we will have. Now tell me, in your minimal DFA, how many states you will have? In the minimal DFA for this language, how many states we have? 3 states we have. 3 states we have. Which of them is final state? Which of these is final state? Yes, this is your final state. Okay, basically you can notice. Okay, this is your final state. So basically you have 3 states. In the minimal DFA for L, I can say in minimal DFA for L, we have 3 states. Okay. So this is, now let me just tell you one thing. Actually, what is happening here? Now just okay, let me tell you. If you have, okay, so this equivalence relation we defined. Let me tell you, this equivalence relation is known as Myhill Nerode Equivalence relation. That's your Myhill Nerode theorem. Okay, so basically this equivalence relation that we have defined on sigma star. Okay, so you have, remember, so basically this is the final summary. I can say, okay, summary, this is the summary. Let me give you the summary. So you have language L. Okay, you have language L. Okay, now what we do, we define we define equivalence, we define relation. We define this relation R, okay? Or we can write it like this. We define this relation R, okay? Either you can write like this or you can write like this, that is your choice. So we define relation R on sigma star. Remember, on sigma star. Yes, Hari Krishna, very good. So can you notice basically this was the method we were using in minimal DFA minimization. In our minimization, basically we were using this method. From here it was coming. Okay, I hope you I will connect, don't worry, I will connect the dots. But the point is, your language L, we define relation R on sigma star, okay, such that W comma X, they belong to sigma star. Now W is related to X if and only if for all Z, for all strings XZ belongs to L. So for all strings WZ belongs to L if and only if XZ belongs to L. So this is our relation. Okay, you understood this relation? No discrete, no TOC required. For this relation, there is no TOC required. This is just a simple equivalence relation on sigma star. This is very simple equivalence relation on sigma star. So basically this relation, I can say this relation, this is a, we have already proven that this is a equivalence relation. This we have already proven that this relation that we have defined, this is an equivalence relation on sigma star. Remember, this is my base set. My base set is this. This is my base set. This is always the base set. Okay. So this relation we have already proven, this is equivalence relation. And this relation R, or you can say this relation R, is called Myhill Nerode equivalence relation. Myhill Nerode equivalence relation. So the name of this relation is Myhill Nerode equivalence relation. Is this clear to everyone? We have defined equivalence relation on sigma star. Okay, with respect to some language. Okay, with respect to some language. Basically, two strings are related when they are true friends. Yes or no? Two strings are related when they are true friends. Correct? When they are indistinguishable. Okay, now you can notice that this. Okay, now you can notice very thing. This is a note. This number, okay, this equivalence class, this relation has finite number of equivalence classes. Finite number of equivalence classes. If this relation has finite number of equivalence classes, then L is regular. Yes or no? Can you notice so many examples we have seen? If this relation that we have defined on sigma star, this relation we have defined on sigma star, if this relation has finite number of equivalence classes, then L is regular, and vice versa. And vice versa means if L is regular, then this relation will have finite number of states. So will have finite number of equivalence classes. Okay. Another thing that you can see, number of equivalence classes, that is same as number of states in minimal DFA. Yes or no? Yes or no? So number of equivalence classes of Myhill Nerode equivalence relation. Okay, can you notice number of equivalence classes of Myhill Nerode equivalence relation is the same as number of states in minimal DF. If it is finite, of course, if it is finite. If number of equivalence relation are, sorry, if number of equivalence classes are infinite, then it is not regular. But I am saying if it is finite, let's assume number of equivalence classes, if it is finite, okay, number of equivalence classes, if finite, okay, this is not visible, right? If finite, okay, if finite, so number of equivalence classes, if they are finite, okay, if finite, then is same as number of states in minimal DF. Is this clear to everyone? Is this point clear?